Hello everyone, welcome to tonight's lecture hosted by the IMechE Railway Division Northwestern Centre. I'm Gareth Tucker, I'm the chair of the centre and the chair of the event tonight. Tonight we've got a lecture delivered by Stuart Hillmanson, who's a reader in railway traction systems at Birmingham University, and Ralph Swaney, who's a principal development engineer at Porterbrook. I'll just give you a few little details, housekeeping details. So you'll see in your workclass screen, you've got the chance to ask questions. So if you just ask a question in the text anytime during the presentation, feel free to just write it in there and we'll then get to them all at the end. This event is being videoed, so if any of your colleagues are missing it, you're going to get a link to the video and you can share it with your colleagues later. I told us best for you to view the screen in full screen mode because there's there's only one or two slides where there's some smaller text and you'll see it better in full screen. So Stuart, like I said, he's a reader in railway traction systems and he's been investigating developments of hydrogen as a fuel for railway applications over the last decade, and he's the academic lead for the HydroFLEX project. Ralph is a principal development engineer with Porterbrook Innovation and Projects team, and he's got 20 years of traction and rolling stock experience, including build, operations, maintenance, fleet engineering, and development of rolling stock gains in a range of companies. And he's leading Porterbrook's work on the hydrogen traction battery technology development. So I'm just going to hand over now to Stuart to deliver that jam.
Thank you very much, Gareth, and it's a pleasure to be here presenting this evening. Normally I have presented at IMechE events before, and normally it's in a nice hotel somewhere. I guess this would have been in Manchester or Derby or somewhere like that. So just imagine you're sitting in a nice hotel and looking forward to the lecture and also probably the drinks afterwards. So it's a shame we can't be all together this evening. The last sort of 10 months has been a slightly odd for all of us, and normally I travel everywhere by train, and in the last 10 or 11 months I haven't been on many trains, but I did spend quite a lot on this train that you see in the picture. So this is the HydroFLEX train, and this evening we'll be telling you the story of why we're doing it and how we got there. So this picture I think is quite iconic now, and both Ralph and I are getting quite attached to it. It's showing the HydroFLEX train travelling across the River Avon as it was moving towards Evesham and braking towards the station. So we were going about 40 miles an hour then, and travelling across that. Ralph and I were probably just staring at some dials and gadgets on board the train and not looking where we were going. So we're quite pleased we got a drone to come and take a picture of us while we were doing that. So it's been an emotional project, and we've achieved a lot. I think the other thing just to draw your attention to is this train is an electric train. So it's running on a non-electrified line, and I think that's a very important feature, that we travelled along without the sound of a diesel engine underneath us and no noxious emissions coming out of the tailpipe. So why? What is this HydroFLEX all about? As Gareth introduced me, he said we'd been investigating hydrogen fuel cells for a number of years and done it on desktop studies and small scale demonstrators and so on. And back in actually RailLive in 2018, one of my colleagues, Alex Burrows, came up to me and said, do you think we could do it on one of Porterbrook's trains? Because he's got some friends there. And he went up to Helen, who you can see in this picture in the middle, in the middle of this picture on the bottom right, basically said, yeah, you can borrow one of our trains. And then, as they say, the rest is history. So we then formed a partnership, which we launched just a few months later at Intertrans with an agreement to try and convert one of these trains to run on hydrogen and a fuel cell and battery system. Unfortunately, Porterbrook, through the likes of people like Ralph, had a huge amount of experience of converting these trains to running on different types of fuel, and had done it with their diesel flex product. So they already had an intimate knowledge of how to adapt the traction system to take in other power sources. So we set about doing this project then in a really quite a short time frame. So what we're going to tell you today, why are we doing this? I'll introduce an overview of HydroFLEX and a bit about mainline testing. And Ralph's going to go into quite a bit of detail towards the end of the presentation on exactly how we interface it with the traction system from particularly electrical point of view. So why are we doing this? There's two reasons really. One is I think the emissions challenge. So the rail vehicles that we've got in the UK, the ones that have got diesel engines on them, a lot of the diesel engines have got no exhaust after treatment whatsoever. So whatever is produced inside the engine comes out the exhaust and is emitted to the air around it. Some of that then is affecting stations, and particularly underground stations are badly affected, or anything with a canopy on it. So air quality is a big driver, but we also have an issue over carbon efficiency as well, and the drive towards decarbonisation. There's another factor which is important. Oops, gone the wrong way. Sorry. Is the energy supply that the UK is currently using. At the minute, we've got most of our energy is coming from low carbon sources, and we have roughly half of it from fossil fuels. But by 2050, that will be pretty much entirely low carbon or zero carbon. So the grid is becoming decarbonised. So this means that we can produce hydrogen from the grid, and we don't need to worry too much about the fact that we have some inefficiencies producing the hydrogen, because the grid is already decarbonised. It just becomes an economic factor. Hydrogen is already produced in bulk in the UK. So BOC, who provide all the hydrogen for the HydroFLEX train, have a number of sites around the UK and are producing it in bulk. It's just something that the general public don't really know about, because nobody needs to buy hydrogen, but it's used as a process gas in a whole manner of things. Are used to produce all sorts of different products. We just buy it, and it happens to end up providing power in a fuel cell. So there is already a huge amount of experience of handling hydrogen and transporting it around the country, and it's done incredibly safely. Hydrogen has also been used to provide traction for buses. There's been buses in London for a number of years, and a very successful project up in Aberdeen that's run for several years. And also we're looking at things like dumper trucks and dust carts and so on. Now the power requirements of these are lower than a train, but they're not far off. So we really taking bus technology and upscaling it and making it suitable for traction on board trains. As I said, we've been doing work in this area for a number of years, and this is, you can't quite see this paper. I'm not expecting you to read it, but it's a paper that was published in the proceedings of the Institution of Mechanical Engineering in one of the journals that the institution is involved with, called the Journal of Rail and Rapid Transit. And I wrote this paper back in, I think it was 2003. So I had started thinking about hydrogen as a fuel source for rail applications back then, and it's taken some time to get to this stage, but I think there's a lot has changed in the world around energy supply, energy security, and the pressing need to decarbonise. So the time is right for this, and that's also coupled with the maturity of the technology. So hydrogen fuel cells now are very, very mature technology. The one that we've got on HydroFLEX is incredibly robust. We've given it a really, really tough workout running a train, and it's coped with everything we've thrown at it. Similarly, the hydrogen storage system is mature technology now, and there's lots of it in application in all sorts of different sectors. So we're in a good time for pushing this technology forward. So I'm going to spend a few moments talking about the train itself, and then hand over to Ralph, who will go into a bit more detail about exactly how the interfaces work. Now, there's some pictures of the train. It's the UK's first full-size hydrogen-powered train. I've got the full size there in brackets there because our team at the university developed miniature locomotives, fifth-scale locomotives for entry into the IMechE's Railway Challenge. And we've done that over a number of years and got a lot of attention for producing those vehicles. The unit that we had, it's nice because it's a 319001, so it's the first unit from the 319 series. It's done about 2.5 million miles, so and it was retired and then came out of retirement and had a very enjoyable post-retirement workout as a hydrogen train. It's a dual voltage train, can take 25 kV overhead or third rail 750 volt DC supply. Ralph will go into this in a bit more detail, but it's very important that we had what's called a DC bus on the train that we could interface our traction system into, and that's the whole principle about how we did this, and it made it very easy. The fact that the train already worked off what was effectively a 750 volt nominal DC bus. So this is a layout of the train, and as this was a prototype project, we weren't intending on carrying passengers, although we have carried thousands of people on it as guests. We decided to convert the motor car into a propulsion system car. So we stripped out the seats and put all our equipment inside the train. There are two reasons for doing this. One is because this was a really short timescale project. We didn't have enough time to package it and put it underneath the train. So it was easier from an engineering point of view, but more crucially, we wanted to set this up as a kind of like a working laboratory. So we were able to demonstrate the vehicle and show when everything was shut down, we could show guests around the carriage and point to stuff, point to the fuel cell, the hydrogen system, the control system, and the battery, which is what you can see there. And people could see firsthand the technology, and that was a big help in terms of demystifying things like hydrogen storage and so on. So people were able to stand right next to the hydrogen storage tanks and see how they work and see how the fuel cell works, where the hydrogen goes into the fuel cell, where the power comes out of the fuel cell, and where it's connected to the batteries and so on. Some pictures of the installation. So this is showing the train with all the equipment removed, and then on the right hand side is us fitting some of the battery system. So we did a lot of engineering work with companies like DG8 who did all the finite element calculations to ensure that how we are attaching all the equipment to the train was safe. So it was all done to GMR 2100 standards, so we could survive, I think it was a 5G shock load, and cope with like overturning forces and fatigue forces. And we did that for our demonstration at RailLive with a view to thinking that we would eventually want to take the train onto the main line, and getting full design calculations done was an important part of that process, and DG8 did a very good job of that. Here we can see the hydrogen storage tanks. So these are tanks which is an aluminium tank wrapped in carbon fibre. We have a 350 bar working pressure. Each tank stores about 5 kilograms of hydrogen, and we've got 4 of them. So we have just slightly under 20 kilograms of storage, and they can run the fuel cell for around about 4 hours. It's designed to standard EC79. And that's technology adapted from the automotive sector. Hydrogen is a bit of a funny gas. It's got what's officially called a negative Joule-Thomson coefficient. So when it's expanded into the tanks, so we refuel it from a higher pressure outside, when it expands, it actually gets warmer. So the gas goes into the tanks and heats up, and it can increase the pressure. So when we're filling these up, we can go higher than 350 bar because the gas expands into it, gets hot, and then as it cools down later, then we'll settle back down to 350 bar. So it's quite a strange gas in that respect. This is a picture of our fuel cell. It come from Ballard. It's produced in Canada, and then it was commissioned in Denmark. So we went over and a very nice few days checking it out in Hobro in Denmark before it came back and got fitted into the train. So this is it shown here in position. And we as engineers were very much thinking of this as a black box. It had inputs and outputs, hydrogen inputs, control inputs, power outputs, and produced power that was fed through a DC to DC converter, controlled with a CAN bus and some other hardware signals that then fed into the main bus line of the train. Here's a picture of the battery. So it's a hybrid system. We had both a fuel cell plus a battery working in tandem. There's actually 2 battery packs, so in effect we had 3 power sources on board the train. The total energy storage of 84 kilowatt hours, and these were used to provide the system voltage of the train. So we designed these battery packs to have a nominal voltage of 625 volts, which is somewhere in the mid range of what the train could work at. Just as a quick slide on how a fuel cell works and why fuel cells are really quite important as a power source. They take in hydrogen into an anode, and air goes into the cathode side of it, and you have a membrane, electrolyte membrane. And on the anode, you have a catalyst, and the hydrogen atoms land on the catalyst, and they dissociate and become protons, or hydrogen positive ions, and electrons. And then the hydrogen ions, or the protons, pass through the membrane. So you sometimes hear fuel cells called PEM fuel cells, which stands for proton electron membrane, and a proton exchange membrane, and the protons travel through the membrane and they go to the other side. They mix with the oxygen, which also dissociates and becomes oxygen ions, and they recombine with the electrons and then produce water. And you can see the electrons actually travel around an external load circuit and producing electrical power in that process. So the advantage of this method is that it's an electrochemical reaction rather than a combustion reaction. So the theoretical fundamental efficiency of this can be much higher than you could achieve through a combustion process. It's not 100% efficient, but we can get up to well over 50% efficiency for this process, which is higher than what you can achieve in combustion. So this is some of the pictures of the refueling system. So we work with a company called Fuel Cell Systems, and the orange tanks there are how we receive hydrogen. This comes from BOC. So we buy these tanks in this very high purity hydrogen, which is required by the fuel cell, and it does cost a lot of money right now, but the cost of these hydrogen tanks should come down in the future. And then we then transferred the hydrogen from that into the van at high pressure. So we pump the hydrogen from 170 bar up to something like 500 bar that goes inside that lorry shown there. And then we can decant that straight into the train and refuel the train in 10 to 15 minutes then with the rapid fuel. So we can get a similar kind of refueling time as what you'd get on a standard diesel train. So that's it from me. I'm just going to hand over to Ralph now, and he's going to take you through some of the in-depth work that we did to interface with the traction system and provide the smooth power flow from fuel cell and batteries into the traction system to get the train moving. So over to you, Ralph.
Okay, thank you very much, Stuart, and good evening, everyone. The fuel cell description is quite interesting. A lot of people can't understand the fuel cell and ask me how it works. I tend to explain it as think of it as a live battery. So rather than having chemicals stored within it, which create your energy, you have to pump the chemicals in and through the battery continuously to create your power output. Sometimes that helps to understand. So. Okay, so moving on to the power system. We have a block diagram here, and if we start top left, we have a Ballard fuel cell creating 100 kilowatts. It's got a lowish voltage for what we needed on the train, so it's about 500 volts thereabouts. So we put that into an electrical piece of kit called the DC-DC converter, and effectively that steps up the voltage and also allows us to control the voltage. So we were able to control the output voltage to match either battery charging or battery discharge to keep a good balance of the battery. So that feeds into what we call the T point of the system, where the fuel cell output and the battery output are T together to feed into the traction system. So on the right, the yellow box is the battery. It was supplied by a company called Denchi. You may not have heard of them. If you head north and keep going to get your feet wet, they're in Wick in the very far north of Scotland, so quite some way away, which did pose some challenges, but by and by it was good. So that's a 65 volt nominal, as Stuart said. it actually fluctuates from something like 650 down to about 585, 590 over its full state of charge. And we're outputting at 125 kilowatts peak, but as your voltage drops, you can't sustain the same amount of power. And I think it's an important point. If we were doing this on a scale version with more power, we'd have another DC-DC converter in front of the battery, so that you could pick a power that you can achieve through the whole voltage range. So our new systems feed it down in parallel to the existing Class 319 system in the grey boxes. The first of which I've labelled line converter, but essentially it's a bridge rectifier rated at 1 megawatt. So a trifling 200 kilowatt wasn't really taxing it. It then passes the DC to a motor converter. Now this is a GTO, I know, quite an old-fashioned system now. We wouldn't build on these days, all IGBTs. But it's an old-fashioned DC chopper system. I'll explain the chopper in a minute. And then the output of the chopper goes to the traction motors, and 4 of them, which drive the train. So, moving on. So a chopper, essentially it's a high-power electrical switch. And we switch this switch off and on with a pulse train, and use what you call an on-off ratio or a mark-space ratio to control the amount of power going to the motors. So you get a very spiky output here on the left, and then when you feed that into the traction motors, the traction motors have electrical inductance, which tends to oppose changes in current, and what you get is this smoothing out effect. So instead of this lumpy waveform on the left, you end up with a smooth, almost sawtooth-like output to current. And the net effect is the area under the curve is the net current that you get into the motors. So as you increase the frequency of the pulses, you get more area under the curve, and then you get more current into the motors. So in designing this train, there was a bit of a problem statement. The train's rated at 1.2 megawatts power on the AC overhead line, and a little bit less on DC, but still substantial power. And we only had a trifling 200 kilowatts available. So it's a very aggressive power system. It ramps up power very, very, very quickly, and it's clear that it would overwhelm our power system if we didn't manage that somehow. So there's just a table there showing you what the chopper, how it switches, and the different notch settings. Notches are the driver's power control settings, and you can see the sort of motor currents it's trying to climb to. So the initial things we did to try and cut that power down was we switched out 2 traction motors. The train had a facility to switch out motors, so we used that on 2 motors only, and we restricted the driver's notch to notch 2, which limits you to 50%. Even at that, it was still quite a lot of power for the train to deal with. So we had another secret weapon to call on. So people in the northwest, which is the IMechE region, will be familiar probably with the northern bimode flex trains that Porterbrook produced. Now they had a similar issue, albeit on a slightly different scale. Their twin engine output was 780 kilowatts, whereas the unit was still 1.2 megawatts, and to a lesser degree they also had the problem of dumbing down the power demand. So they had to develop a means of limiting this. What they did was we looked at the existing traction system. This is a typical closed loop control system. You input the current you want from the system. The chopper creates a waveform, and you get power into the motors. But the closed loop feedback trick is to actually measure what you're getting at the motors and feed it back into the system to fine tune or adjust the value you want. And that's a continuous process of set, measure, and then adjust based on the feedback. And this device here is the CMD, or the current monitoring device. So the clever thing that Brush did on the bimode flex was they intercept this feedback signal, and they were able to adjust that signal and apply a gain factor or a multiplication factor to fool the traction system into thinking it had the power it wants. So as an example, I showed you in the table earlier, notch 2, the system's increasing the chopper to try and get 470 amps in each motor. So if we were somewhere about 300, 310 amps, we apply a multiplication factor of 1.5. So the signal going back in the system says, yeah, I've got 470 amps, I'm fine, you can stop increasing the chopper. And this is how we actually manage the power system in the train and stop it from overwhelming our meagre power output. So I hope you can see this, it's not too small. It's an example trace of some of the testing work we did at Long Marston. The blue trace at the top is the traction motor armature current. The red one is the speed, maxed at about 20 miles an hour on this run, which is about the limit of the track at Long Marston. The green line here is the CMD. Now, this was fully manually controlled at this point in time when we were doing the RailLive testing. And I had a control box and I was twiddling a potentiometer, trying to adjust this green trace to keep the purple trace at the bottom, which is the line current, under a threshold of 360 amps, which is all we had to play with. And that was quite a fast ramp. It was quite difficult manually to actually keep up with that and keep it within the limits of the power system. We didn't always get it right. Occasionally we didn't manage it and the battery or something else would say, no, that's too much current, and it would just shut down. That happened a few times, unfortunately. So this is an example of the control unit I was talking about. On the left, you can just see it on the picture on the right behind the left-hand laptop, but essentially I'd sit there with my headphones on, looking at the screen, watching the current trace and tweaking the adjustment pot to try and stop the train exceeding its power limit. Now obviously that's not an ideal situation. The box had an automatic control feature on it, but at that point in time we didn't have enough confidence in the behaviour of the system to know how that was going to react. So people were quite used to me sitting there with the headphones on and twiddling knobs, and actually my radio call sign became DJ Ralph at one point. DJ Ralph, go spin your dials. So with that experience, we were then able to set it up better for the mainline version. So yeah, we did, after initial testing, we had the RailLive event, which Stuart mentioned, and we were carrying quite a number of visitors on numerous trips each day on a short section of the test track at Long Marston. We even had the rail minister on board. I've forgotten the guy's name. It's a revolving door at the Department of Transport. You can never remember who it is at any one time. And we had the BBC on board as well, doing some interviews with my colleagues. So, RailLive, ticking the box, that was phase 1.0. Phase 1.1 was moving on to mainline testing. So, Navy UK were very impressed with the work we'd done at RailLive, and we got some further funding to support the paperwork and approvals work to try and get our train on the mainline. It was meant to be completed by 2020. Obviously, a little small problem called COVID came along and upset our plans for that. But nevertheless, it was quite a task list to work through in terms of getting the unit compliant to go on the mainline. So there's a few, I won't read them all out, but the key things that I'm going to touch on are the traction control, the technical improvements. So yeah, there's a few technical changes. Clearly, from what I described earlier, the setting the power control was not ideal situation, and certainly not repeatable for any length of time on mainline driving. So we had to get the power control automated. And to feed that, we needed to understand what the limits were in the system. So depending if your fuel cell was up full or your batteries were both online, you may have different powers available. So we had to have a system of, excuse me, determining what systems are online, setting an appropriate power, and then managing the output of the fuel cell accordingly. So a few other things in that. Weak field is another thing we added. I'll explain that in a bit. So there's a few technical changes to the train inputs, and also the university software had to be modified to get the battery limits under tighter control. So this is the key piece of hardware that we had to develop for the mainline. Looking from the top, the three LEDs on the right here, the three green ones on the box, are telling you which power system is live. So I think it was fuel cell OK, battery 1 OK, battery 2 OK. And then various buttons and lamps indicating when the driver's taking notch 1, notch 2, etc. And what we did was we had some control relays in here which inserted a short time delay into the notch. So, for example, driver pulls notch 1, we pause a second while we signal the fuel cell to ramp up its power output, and then we let notch 1 into the traction system, which behaves as normal. And there's various time delays to allow fuel cell increases at different notches. We also changed the wheel slip management on the train. Class 319s have a very binary wheel slip system. It's quite good at detecting wheel slip, but it just kills power completely. And then when it sees slip stopped, it just puts power back on in full. Now, that's very rough and very aggressive way to try and manage wheel slip. And what ends up happening typically is you cut power, and as soon as you apply power again, it spins again. So it's not a very good. So we took the opportunity to put in some what I call a notch reversion technique, which basically meant if you're in notch 2, it knocks back to notch 1 when you got wheel slip, to give the wheels a chance to recover and stop slipping, rather than the binary and very rough, fully cut off and fully put it back on again. So, just a funny story. When I spec'd this line light for the top of the case here, I wanted something we could see through the length of the vehicle if we were up the other end managing batteries or whatever. I wanted something that was quite visible. So I spec'd a red light originally, and it's quite hard to find 110 volt lamps. They're not common, that are not flashing. Usually they're flashing ones. But I found this red one and spec'd it. When the guy built this panel in the workshop and turned it on the first time, he promptly fell over backwards in astonishment, and it lit up the whole workshop quite brightly. And he was at that point we decided perhaps not a great idea to have a really, really bright red light on the railway, so we swapped it for a blue one. So I mentioned something called weak field. One of the problems with DC traction motors is when they start spinning up to speed, they become part motor, part generator. And unfortunately, the generator part, the voltage it creates opposes the forward voltage of making it motor. And you get to an equilibrium point at which you can't get any more power into the traction motor. So something has to change. And you can see an example in the trace there. That's like a notch 1 curve there. The driver goes to notch 2, current jumps back up again, but then apart from where you switched off there, you can see if you extended the line out, it would flatline, and you'd be at terminal velocity at that point. You just can't go any faster. So that point was likely to be quite low speed for us in notch 2, somewhere about 35 miles an hour, something like that, which is going to quite significantly limit our line speed on the mainline. So we did something quite unusual. We looked at something called weak field, which is normally applied at quite high speed on a 319 applies at something like 60 miles an hour when it's on full chopper. It uses this to get an extra sort of boost of power. So what it does is it reduces the current in the traction motors so that there's less of this reverse voltage being created, and allows you to get more energy into the motors and speed up. So going back to the actual mainline certification, to quote a TV program, paperwork. There was just so much of it to do. It was quite daunting at times. So we followed the standard common safety methods and as the usual approvals bodies as were involved, and consulted ORR to make sure they were happy with our approach so they could agree that the train could operate. As per the common safety method, we had a hazard identification session, and this generates lots of work. So there was 175 hazards came out of that session, and everyone had to be closed out with a written argument and sometimes other implications, like implications on maintenance or design, etc., etc. So they ended up with 177 different pieces of documentation to close out these hazards. And I think there was about 105 engineering drawings as well to support the project, so lots and lots of paperwork. More approvals, 11 different technical standards, and trying to meet these 11 standards, there were 69 different technical questions, which some of them had single answers, some had 2 or 3 iterations to get the answers to the approvals body's satisfaction. Whole list of stuff here. The network rail part, they had another 10 or so questions which needed answers and responses. Quite an iterative and long-winded and slow process. And not forgetting our own internal change control process and convincing people who are backing the system that it was a safe train to work. So just a little footnote there. This is quite unusual territory for a ROSCO like Porterbrook to be an integrator. Usually OEMs like Bombardier, Alstom or Tier 1 suppliers would do this kind of work, so it was quite an unusual place for a ROSCO to find itself. So part of the approvals is EMC testing, and you can see some pictures here. There's some rather strange looking aerials here pointing at the train, which we had to drive past on full power, and they analyse the waveforms from the train and make sure they're compliant with all the various signalling standards and etc., which are listed a few down below. On the right, there's just another view of the control area, the operator's area, and you can see the famous line light, not blinding anyone in this case. So here we've got a short video just to indulge ourselves a little bit on the first mainline run. So enjoy.
So HydroFLEX is the UK's first hydrogen train. It's also the world's first bi-mode electric hydrogen train, and today has been a historic day because it's been the first day we have seen a hydrogen train running on the UK Mainline Railway as we left here at Long Marston and went up to Evesham and back successfully.
It takes a lot of work to get a hydrogen train to run on the main line. There's a huge amount of safety approvals work that we have to go through. We've had to formally document a lot of things, record things, assess the hazards, assess the risks.
Hydrogen is really important in terms of being able to offer decarbonisation solutions to the rail industry, mainly because you can produce hydrogen from renewable sources by electrolysing water. And hydrogen is going to be used on the parts of the railway which are just not economic to electrify.
I can't describe how proud I am of the whole HydroFLEX team to get the first UK mainline hydrogen train working. It's been an absolutely fantastic project, and it's a personal highlight for me as a career, and also it's a real big step forward to the UK and decarbonisation of the railway.
One of the best things about being at the University of Birmingham is we do really, really good practical and industrially focused research, and we've always had a record of doing that. And we developed this partnership with Porterbrook just over 2 years ago, and Porterbrook, from my point of view, have been a really innovative company and willing to take a risk on the technology and working in partnership with us to get to where we are today with the HydroFLEX train.
It's been so exciting for the team to draw together all that work that we've put in and to see it running at a high speed on the network, and more importantly to the industry to demonstrate this technology is the future.
Okay, hope you enjoyed that video. A few more pictures here, enjoying the moment of our first mainline run, which was a really exhilarating, exciting time for the team. So on the left you can see, I don't know if you can see, but the speedo's just a smidgen under 50 miles an hour in that picture. As I said earlier, we expected the traction power to kind of flatline round about 35-40 miles an hour. But the wheat field worked an absolute treat, and we're actually a pleasant surprise to be touching 50, which is a real achievement, much to our surprise. On the right, you can see it's passing an IEP train. I was going to title that Old Passing New, but actually our train was old, but it had a lot of new bits on it, so it was kind of new old passing new. Yeah, anyway. Some more pictures. Arrival at Evesham the first time, which is a historic moment. The last time that train had been at Evesham was on its way into Long Marston, towed by a Class 37 or something to go into storage. So a triumphant return, I think, would agree. And the first trip, top right, you can see it just coming back through Evesham station. And then on the first trip, we seemed to manage to get a busy day at Long Marston. There was lots of traffic on the branch with stock either being taken in or taken out of Long Marston, and also Viva Rail running their battery train up and down. So we had to sit in the sidings and recess for a bit, so it gave us a good photo opportunity. Well, photo opportunity for the people with the PTS, which was not us, it was the driver crew. So just touching back on the Wakefield thing we talked about, the middle graph here in green, you can see the speedo just under 50 miles an hour, but we did have a known issue with the speed input in that car was 1 or 2 miles an hour under, so we knew that was slightly under the speed. I don't know if you can make it out on the purple trace. The purple trace on the top graph is the line current, and there's a step up just about the 40 mile an hour mark, and that's where the Wakefield kicked in. It's almost like a gear change. It gives you another boost on torque and actually gives you a bit of a burst of speed, and you can actually see the graph climbing a bit after that point and getting to our amazing 50 miles an hour point. So this is the Birmingham University data logger as well, and again you can see a big step up in current associated with the Wakefield change, and then another small step up later on around about 3,400 seconds. I think that's actually the compressor kicking out. It's quite a significant load in the system, the compressor, so it will give us an extra bit of power when that's switched off. So this project was an amazing collaboration of lots and lots of parties, and most of them hopefully are captured here in this graphic on the right. But we couldn't have done it without everyone pulling hard and working really rapidly and overcoming various obstacles to pull together and create a really, really marvellous project, which nobody will forget in a hurry, I don't think. So what's next? Well, I mentioned phase 1.0 and 1.1. Well, now we're moving on to phase 2. So this is the mainline, the third mainline day. That's Grant Shapps, so you can see the current Minister of Transport. Talking to, that's Mary, our CEO, Mary Grant, with her back towards you, the blonde hair. That was at Evesham. We gave a taxi ride down to Long Marston. So Innovate UK are really pleased with the work we've been doing on hydrogen, and they've now given us further funding to try and make it more of a productionizable setup. So we're trying to get as much equipment as we can underneath the floor, although it's a challenging and limited space. We're doing what we can there. So we're trying to, the next unit will be another 319, but a different one, and it will have fully retained bi-mode functionality. Better, maybe 75 to 90 top speed in hydrogen, standard electric speed. And we're trying to get towards a typical DMU's daily range with this somewhere between these two figures, hydrogen on board. We're still working that design at the moment. Yeah, so we're going to use more parts of the bi-mode flex concept in terms of driver controls interfaces to build on the learning they have. So just to wrap up, some takeaways. The infrastructure in terms of hydrogen supply and refueling is getting quite challenging, especially the scale we're pushing things to. Storing it on board is extremely challenging. As Stuart showed you, 4 tanks, they weighed about 100 kilograms each, and they had 5 kilograms of hydrogen each, and we need 2 to 3 or maybe even 400 kilograms, which is really challenging to incorporate that in the space inside a train. What we really need is higher pressure tanks, which are way off at the moment. Safety and approvals is challenging, but I guess people's perception and interpreting the safety and approvals requirements is skewed by the perception of risk, and that makes it a bit more difficult for us. And the final takeaway was it was a massive career highlight for lots of people on the team, and something myself and Stuart, I suspect, won't forget in a hurry. And I think that's everything. Thank you for listening.
Thanks, Ralph and Stuart. We've got quite a few questions coming in. Hopefully we'll be able to get through them. So just bear in mind when you're answering, there are quite a lot of them when you're taking the time to answer each one. So I'm just going to read them out, and then either Stuart or Ralph, I guess you'll know between you which one is the best to answer, or you might both have an answer. So there's a question about fire safety for carrying hydrogen. Is there any rules you had to meet when you're doing the approvals, and what did you have to do, anything special to meet them? And also, is there any particular issues with going through tunnels or longer tunnels when you're carrying hydrogen?
Stuart, can you cover that? I don't know if you're talking, Stuart, you might be on mute. Okay, I'll try and cover. Stuart's not there.
Okay.
There's no fire suppression required for hydrogen, because basically if it does catch fire, you've not got any chance of putting it out, to be honest. There's no suppression systems that would put out a hydrogen fire. There are some requirements, the general material requirements for things used in modification applied, but there's nothing specifically for fire. It's all about prevention rather than trying to put it out.
Great, yeah. Got another question here. This is from Darren Bell. It's maybe a bit of a tough question, but have you got an overall idea of the total cost of operating a hydrogen train? You know, when you take into account the fueling and whatever you have to do in depots or stations to accommodate them in future.
Yeah, that is a tough one.
Yeah, sorry.
I don't think we understand at the moment. Until we start generating hydrogen at scale for rail, we don't really know what that cost look like, because there's nobody remotely on that scale at the moment. This is the problem.
Yeah. I guess it's just storing it and transporting it is the cost. Got another question here from Raphael Tudala. So you mentioned in the presentation that the main idea is these trains would replace diesel trains on routes that are hard to electrify. Do you think there's also any potential for replacing, current electric trains that are currently driven, collecting their power through the overhead line or through third rail?
No, hydrogen will never be as efficient as straight electric. Never going to compete with that. I think the niche market for hydrogen is non-electrified lines that are either too remote, don't have the traffic to sustain or to support the cost of electrification, or it's about cost and passenger numbers that just won't justify electrification. I think that's where hydrogen's got a niche. It's never going to be high speed, high frequency, high cost. High numbers of people. That's not the kind of market it's for. Electricians are much better at that.
Can I add something in here? Just to add to that, Ralph. One thing Ralph mentioned at the beginning was that the train still retains its electrification equipment. So I think there's a big scope for using these types of vehicles on electrified lines, and then providing range extenders off the line. So there's plenty of services that would really work quite well on.
Yeah, that makes sense. Great. I've got another question here from Carl Land. So it looked like you're still using the standard traction motors on the train, and you've added your system on top, and he's asking, did that cause any problems with the traction motors and that bit of the traction system that's still there? And is the plans in your next version to use different motors or different traction system?
Yeah, I used to be a fleet engineer on 319s at West Midlands, and I understand just the kind of problems they're talking about traction motors. They're not the best. But the premise of the flex conversion was not to re-engineer the traction system. Notwithstanding some of the problems, it's generally sound, and we could have looked at modifying the software and control system, but that's a huge expense and a huge time penalty and requalifying software. So I think adding the engines is quite a significant cost in itself. So I didn't want to make it a more complicated project by changing traction as well.
Yeah, just to add to that, I think one of the benefits of this type of vehicle was it had a DC link on it. So our fuel cell and battery system just interface with the DC link, and really it doesn't really matter that it's a chopper controlled series wound DC motor. It doesn't care about that too much. Obviously, Ralph's done all the work on making sure the traction system can work with our propulsion system, but the drive system can easily be used on other types of traction, so it'd be quite easy to adapt this to running on an inverter driven AC traction motor train as well.
Great, thank you. I've got another question here from Olawale Kuti, and he's asking, have you considered alternative fuels, like rather than hydrogen for the fuel cell? And he's suggesting ammonia, NH3, which might have a higher energy density. I don't understand any of this. I'm just asking the question.
I think the answer to that is we're fairly agnostic about the source of fuel. I mean, we're aiming to produce a autonomous vehicle that can get a mobile fuel which can be produced from renewables, and in this case we've used hydrogen. I know ammonia is actually quite a good way of storing hydrogen, and if there's a technology that comes along that would allow us to use ammonia in a fuel cell, maybe a solid oxide fuel cell, or equally reform the ammonia into some nitrogen oxide or something, and hydrogen, we would be able to do that as well. So we can be agnostic about this, and if technology comes along that will work like that, then we'll use it. But right now, I think the standard the standards for hydrogen storage and fuel cells are of such a level that the mature technologies, and it was very much plug and play. We only had the equipment installed in the train literally weeks before it was moving the train forward, so it was very much plug and play at a high level of technological maturity.
Great. There's a few questions around battery trains, and so what's the kind of comparison between a fuel cell hydrogen chain and a battery train in terms of like range and size of the equipment you have to put on the trains?
That's quite a good question. So,
yeah, you go first. All right. So a battery train can give you range of around about 100 kilometres, or something like an hour's worth of use if you size the battery right. So if you have a battery train, it's going to have to be a dual mode train where it spends it predominantly under the wires or connected to electrification system, and can do short hops in between electrification systems. Lots of these trains have been developed in Germany now, and probably will be very successful there. But for a hydrogen vehicle, you can store a lot more energy than you can do in a lithium-ion battery, and we're looking at ranges up to like 1,000 kilometres with sort of running speeds of 140 or even possibly 160 kilometres an hour. So a hydrogen train can have a decent amount of range, which allow you to do a day's duty cycle. However, it can't really compete head-on with diesel, so you can always shove more diesel in and store more energy in diesel than you can with hydrogen. So we'd struggle to kind of replace the likes of the Class 220s with a hydrogen vehicle. So if we want to do Penzance to Aberdeen with hydrogen, we just can't do that right now. Certainly not running at 200 kilometres an hour either.
I think just to back that up, the two things have different challenges. hydrogen and batteries, they're both difficult to package on trains, but for different reasons. Batteries are very dense and very heavy. Hydrogen's the opposite, it's very voluminous. It's a volume challenge. So you've got a volume challenge on one hand and you've got a mass challenge on the other.
Well, we've got time for a couple more questions, so I can't read out every single one on the list. I'm just going to choose a couple here. So I've got one from Fatumata Kasama, who's asking about hydrogen prices in future. So it sounds like you're expecting the hydrogen price to sort of go down in the future. And is there any published research on that, or what's that based on?
Yeah, there's an enormous amount of interest in hydrogen now, and I think what will happen is other markets, other sectors which are trying to decarbonise will actually drive the prices down. So rail's always going to be a small market for hydrogen, but if you look at heavy goods vehicles, it's going to be impossible to decarbonise heavy goods vehicles with batteries. It won't work. So I think there's a huge amount of interest in decarbonising heavy goods vehicles, and that can be achieved with hydrogen. And you just need to look at what happened when we had the delays at Dover, how quickly that airfield filled up with a day's worth of heavy goods vehicles. So once that's happened, the price of hydrogen is likely to come down to less than five pounds per kilogram, which will make it a really attractive fuel for all sorts of mobile applications. And since we've been doing this project, certainly at the university, I get routinely contacted by people offering to who really want to supply kind of tons of hydrogen a day to large markets like the rail industry, and have got the technology to do that. So the price will definitely come down and be economic for rail vehicles to run their vehicles on hydrogen.
Yeah.
Thanks.
Well, I'm going to ask one more. So this is from Razvan Apatry. He's asking, does the fuel cell kick out a lot of heat, and what do you have to do with that?
Yes, it does. It kicks out an enormous amount of heat. And we had a very large radiator on the side of HydroFLEX 1. And yeah, HydroFLEX 2, accommodating the radiators is one of the biggest layout challenges we have, actually. Finding space to get the cross-sectional area we need for radiators is quite challenging. So you're absolutely bang on. It is difficult to manage the heat rejection, and quite a significant problem.
Yeah, so just to back that up, the fuel cell's around about 50% efficient. So we're looking at running at full power to get rid of 100 kilowatts of heat. And one of the challenges is that the coolant temperature that we're using needs to be around 75 degrees at the exit. So it's a fair bit lower than what you'd have in a combustion engine. So that means we need to use a lot higher volume of coolant through the fuel cell than if it was running at 90 degrees heat rejection. So that is a challenge with fuel cells, is to keep them cold. And on the HydroFLEX terrain, because we were running it in the summer, we did the calculations for what happens if we have 40 degrees ambient temperature. So we've got the ability to run HydroFLEX at 40 degrees Celsius at full power and reject all the heat into the atmosphere under those conditions. But as Ralph said, it is an issue. But I think going forward, equally, we can be quite clever with that heat. Maybe there's something that we can use a heat pump to extract that heat and recycle it into the vehicle, or recycle it into the vehicle directly. So in colder weathers, we don't necessarily throw it all away. It can be used for saloon heating, possibly.
Great. Okay, I'm going to have to just bring that to an end now. There are a few more questions which you didn't get to, unfortunately, but I just want to make sure we do finish on time. So thanks, Stuart and Ralph, for a really interesting presentation. It's obviously a very live topic. I've seen the train on the telly quite a bit, which is great, in the news. It's really interesting lecture. Good to know that the railways are doing all this work, working towards helping the country's carbon targets. Really interesting for me to see, like, understand what a fuel cell is and how it works. It's a sort of term we often hear a lot about, but no one ever tells you, unless you're working in it, what a fuel cell actually is. Ralph, I really liked your explanation of the traction control and power system. So, like, you put it in a nice way that us mechanical engineers can understand.
Thank you.
Yeah, so it was just a really interesting presentation all round. Normally we'd give you a round of applause, but obviously you're not going to hear the people on the other side that's doing the applause. So just a few announcements for everyone listening. The next few events we've got coming on, we've got on the 9th of March, we've got our Future of Rail Young Engineers presentation competition. So I'd really encourage any young engineers out there to enter that. If you have a look keep a lookout on our Facebook lines and our on the website, the IMechE near you. We've got our events on there and on LinkedIn. So that's on the 9th of March. Topics presentating for 15 minutes. This is the regional Northwest heat. Winner gets £100, second place gets £75, and if you win, you also get a chance. You get invited to the national competition where there's a chance to win £1,000, which isn't bad for 2 20-minute presentations. Then coming up on the 31st of March, we've got a presentation from Andrew Marden at Northern on the new trains for Northern, and then the one after that is on the 13th of April. All of these are online and you'll get all the links through the website and email in the flyers. We've got 13th of April, Japan versus UK rail model, and that's delivered by Felix Schmidt, who's the chair of the railway division this year, also from Birmingham University. So thanks everyone, and hope to see you all at one of our future events.